All right, welcome back, focused learners. Today, we are literally strapping in and stepping right into the pilot and command seat of a Bombardier Q400. In this explainer, we're running a full-on cockpit simulation focused on one of the absolute most critical aspects of aviation safety, and that is adverse weather operations. Specifically, we're going to master exactly how to handle icing and turbulence in the Q400. Let's get into it.
Okay, let's dive into this. Consider this our pre-departure briefing flight plan. We'll start with icing conditions and restrictions, then defining types of turbulence, turbulence penetration and actions, holding patterns in turbulence, clear air turbulence avoidance, and finally, minimizing CAT flight effects.
Starting off with Section 1, Icing Conditions and Restrictions for our Q400 pre-flight.
Picture this. Our Q400 is sitting on a freezing, snowy tarmac. The weather is closing in fast, and we're running through our pre-flight checks. Now, when we're operating under known or even just expected icing conditions, the flight manual rules, they are absolute. We have to physically inspect the aircraft for icing before takeoff and apply the appropriate de-icing or anti-icing treatments, exactly as detailed in OMA Chapter 15. A really great memory trick to use here is coatings kill. If frost, sticking snow, or ice coats the wings, the control surfaces, or adheres to literally any structure that could mess with our performance, you do not take off, period. We always follow the strict procedures in our flight crew operating manual. And you know, it's not just the aircraft surface we have to worry about. It's the ground beneath our wheels, right? If the surface braking action is reported as nil or poor, taxiing, takeoffs, and landings are strictly prohibited. Just remember this simple phrase, nil or poor equals a no-go at the door. Don't even attempt to move the aircraft.
All right, moving right along to Section 2, Defining Types of Turbulence. Basically, knowing the skies.
So, let's transition from that snowy tarmac up into the air. Turbulence is basically this disturbed, irregular flow of air packed with whirls, eddies, and waves that just subjects our Q400 to random, unpredictable motions. To memorize the threats we face up there, just remember the acronym COSU: convective, orographic, wake, and clear air. First up is the C in our COSU mnemonic, convective turbulence. This is caused by thermal instability in the atmosphere. What's absolutely crucial to understand here is the sheer violent force this places on the aircraft. We are talking about extreme air motion with vertical speeds rocketing up to 6,000 feet per minute. It's an incredible amount of vertical force that demands total respect. Next is the O, orographic turbulence. This happens when rough terrain, specifically mountains, disrupts the airflow. As the wind flows over the peaks, it creates these massive rolling mountain waves, specifically found on the lee side or the downwind side of the mountain range.
Then we've got the second C, clear air turbulence, or CAT. Now this one is of special significance because it is a completely invisible danger. I mean, there are zero visual cloud warnings, it's caused by large wind shears with rapid changes in wind direction horizontally, vertically, or both, and because you literally can't see it before you hit it, knowing how to anticipate it is vital, which we are definitely going to cover shortly.
And finally, the W, wake turbulence, which most of us just call jet wash. This forms behind an aircraft as it passes through the air, and it mainly consists of these really dangerous wingtip vortices. What makes this so incredibly lethal is that it's especially hazardous near the ground during takeoff and landing. If you get caught in wake turbulence at a low altitude, the aircraft's proximity to the ground makes a timely recovery highly unlikely.
Section 3, Turbulence Penetration and Actions. This is your pick checklist.
As the pilot in command, look, your first goal is always to plan a course or altitude deviation around significant turbulence. But hey, if course deviation simply isn't possible, we have to assertively follow our Q400 procedures to penetrate that rough air. Here are the exact sequential actions you've got to take right before penetrating. Step 1, switch the fasten seatbelt sign on well in advance. Step 2, the flight crew must securely fasten their seat harnesses. Step 3, as the PIC, determine and establish your best penetration altitude, heading, and target speed. Step 4, set your thrust to hold that target speed and use the autopilot to your best advantage. Actually, if the autopilot is off, you absolutely must maintain the yaw damper on. And finally, Step 5, use your ailerons as necessary to just maintain a wings-level attitude.
Now, what's really interesting about this slide is how we can correlate precise temperature changes directly with the physical chaos happening back in the cabin. Look at the total air temperature, or TAT, changes. A shift of about 3 degrees, that indicates light turbulence, where occupants just feel a slight strain. A change of about 6 degrees means moderate turbulence. You really want to avoid flying through it if possible. Occupants are going to feel definite strain and unsecured objects are getting tossed around. But a TAT change of about 9 degrees, that is severe turbulence. Occupants are violently forced against their seatbelts, walking is impossible, and as the PIC you must immediately make the PA announcement, cabin crew, take your seats.
Section 4. Holding patterns in turbulence.
So, picture our Q400 up in the sky, unable to land due to weather, and we're entering a holding pattern while being heavily buffeted by rough air. How you configure the aircraft right here is absolutely critical. If you're holding with flaps extended, you require much greater protection against stalling than normal. You've got to accelerate to a speed that is close to but absolutely does not exceed the flap placard speed. However, if the turbulence intensifies beyond moderate, the rules completely change. It's recommended to pull the flaps up, hold at your designated turbulence penetration speed, and immediately inform air traffic control of your situation.
Moving into Section 5, Clear Air Turbulence Avoidance. It's all about reading the charts.
Because clear air turbulence is completely invisible out the cockpit window, we have to read the weather charts before and during the flight to avoid this hidden threat. And this brilliantly illustrates the specific numerical thresholds that act as massive red flags for CAT. We are looking for jet streams stronger than 110 knots at their core. On a 300 millibar chart, if 20-knot isotox are spaced closer than 60 nautical miles apart, you have sufficient horizontal shear for CAT. If vertical shear is greater than 5 knots per 1,000 feet, turbulence is highly likely. And look at the temperature. If 0-degree isotherms are closer than 2 degrees of latitude apart, brace for impact. Oh, and always be highly suspicious of curving jet streams and sharp pressure troughs.
Which brings us to Section 6, Minimizing CAT Flight Effects. Let's talk in-flight corrections.
All right, so let's say we've done our absolute best, but suddenly, bam, the Q400 hits that first unexpected ripple of rough air. We need to make immediate in-flight corrections. The second you feel that ripple, adjust to the recommended rough air speed immediately. If you encounter jet stream CAT with direct head or tailwinds, you've got to change your flight level or turn. Here is a brilliant trick to memorize so you can easily find smoother air. South in the north, north in the south. Meaning, turn south in the northern hemisphere and turn north in the southern hemisphere to find more favorable winds. And if you happen to hit an abrupt wind shift in a sharp pressure trough, establish your course across the trough rather than flying parallel to it.
But wait, what if you encounter CAT in a crosswind? In this case, changing course isn't really as helpful because the rough area is pretty narrow across the wind. Instead, you need to watch your outside temperature gauge closely. Here is your vital mnemonic for crosswinds. Temperature falling equals descend. Temperature rising equals climb. Now, if the temperature is remaining constant, it means you're likely hovering right near the core of the jet stream, in which case you can just climb or descend as convenient to get out of it.
So we're wrapping up, and the crucial point is this. You know the conditions, you know the physical actions to take, and you know how to read the charts. But I want to leave you with this final critical thought. If you are getting violently battered by severe turbulence and air traffic control tells you they cannot approve your requested route or altitude change, are you prepared to use your emergency pilot and command authority, break from ATC, and take the immediate, decisive action necessary for the safety of your Q400 and everyone on board? Think about it. Thanks for joining me on this explainer, Focus Learners. Keep studying and fly safe.